All right, if you would, um, as we look at this, we're looking at gears today, and if you would have your book open to page 692, where you can underline and circle some things maybe to remind you different terms, technique. For transmitting power, gears are used when we need to have a real positive transfer of the power. Okay, so because they're rugged, they can last a very long time, and there's actually a 98% efficiency, as it states here, just almost 100% efficiency transmitting the power, whereas a belt doesn't have that, it slips a little bit. Belts do. They can have vibration as well.
And they break sooner, wear
Right.
out faster.
Yeah. So gears can last a very, very long time. I mean, we got some really old machinery out here. Has the original gear set in it. You know, they might be 40, 50 years old. Got a lot of gears in your engine, your car engine, and the amount of torque and stress that's on those. You know, they're made out of very strong material, steel, special alloy that makes them last a long time. They don't wear out. Although it adds weight, to a machine, so you have to trade that off. You know, you can use a lighter material, but then you're looking at the gear wearing out sooner, because if it's a lighter type of material, maybe even a non-ferrous material, then chances of it breaking, wearing out sooner increases. So you have to trade off sometimes in that regard. So the materials that gears are made out of, basically about anything. Iron, steel, brass, various bronze alloys, and plastics, nylons. So just about any material. Sometimes you need it to be a quiet operation, so you might make it out of a plastic. Or it's a light duty, and not very much horsepower or torque. So you might use a plastic type material. Now, they don't mention aluminum, but there are some aluminum type gears. Okay, they don't last very long, and they have to be very, very light duty, kind of like plastic. And when you select a gear, we do it through a vendor's catalog. So I'm going to pause for just a second and go get my catalog. There's not a whole lot of different gear manufacturers out there, for obvious reasons. It's a pretty complicated process to make one and to mass produce them. So one company is called Dodge, no relation to the car manufacturer. Okay, so they're all online anymore, of course, but give you an idea, of the complexity of it and the range of offering. This is the size catalog, about 1 inch thick and very fine print and application for all types of gear ratios, different types of gears, different types of performances. So you got to know what it is you're trying to do, what kind of power you're trying to transfer, what kind of power, and how you want to use it. So the American Gear Manufacturers Association that you see listed on the screen. There is AGMA 2000A88 standard, and has all the classifications, tolerances, measuring, the spur for spur and helical gears, and of course the metric equivalents for that. Then in ASME, formerly our American National Standards Institute, there is standards for drawing gears, okay, and how they're to look when we put them in our technical drawings. They go from very detailed, where we draw every tooth and show it exactly what it looks like, or we just use phantom lines to represent the outside diameter and the pitch diameter. We'll put gears together to transfer the power, and this is called a gear train. It can be as basic as just 2 gears meshing together, and to increase or reduce speed, we can actually use it to change the direction of motion. Okay, so here you see one gear turning counterclockwise, and the other one, of course, to mesh with it, will turn clockwise. Okay, so you have to remember that. 2 gears together, one is going to be turning the opposite direction. Okay, just because that's the way it moves together. That's the mechanical action. Looking at the gears, this same graphic is on page 692 with the full descriptions. So this is kind of enlarged. I'm not sure it's perfectly proportional to an actual gear, but it gets the job done. So you can see we have an outside diameter, a circle that would encompass the complete gear form. The face width, that's the face of the tooth. Then most of them will have some kind of hub. This is an extension of the inside diameter for the shaft to insert, and strengthens the gear, gives a greater contact area to the shaft. It has a hub diameter. Then there is a bore, the size shaft that fits in there, and that is determined by the amount of horsepower that you're going to transfer. You don't want to overdo it and have too large of a shaft connecting to it, you know, and actually be wasted material. You don't want it too small and twist off the shaft or break the shaft. So there's formula for determining what size shaft to use. Okay, then to attach the gear to the shaft, we have a key way that's cut into the shaft, the bore that is, and then a key that's mounted into the shaft and locks those two together. So that locks the rotational or torsional motion, the circular motion, and then the lateral motion, so that the gear doesn't work its way off of the shaft, because most of them can just be lightly tapped on, and some of them just pushed on with your hand. We have a set screw. Then there's the face, okay, right here, this portion, where it looks like a gear tooth, this face, that's the gear face. So you got the face width and then a gear face. Okay, then we just suddenly we'll look at splines. They're kind of like a gear, okay, and we use it when it's it can be used with a pulley, it can be used with belts, but sometimes when the pulley wheel, or sometimes even a gear, needs to slide on a shaft, or any kind of circular motion also needs to go lateral. We might use a spline. We can also make them where they don't slide. And of course, there's more contact area, so it's stronger than keyways and keys. Let's see. So you'll have to, I'll have to, at the end of this presentation, I'll look up some splines for you. Because they really don't show you any. But it looks a whole lot like a gear tooth, but usually they're square. They're not rotating, contacting other mating gears or anything. So spur gears is the common type, prevalent type you'll see, and it transfers between parallel shafts, and you can have an external gear like this or an internal gear like that. A spur gear is very economical and simple, easy to maintain. It has less load capacity and higher noise levels though. In your car, both in the front wheel drive and the rear wheel drive, you have a differential, they call it, where we transfer the energy from the transmission to the wheels. And they use a special type of gear in there called a herringbone or a hypoid type of tooth, and it has a longer contact area, okay, a larger contact area. So similar to a helical gear, okay. Here we have helicals. The teeth are cut at an angle. You look at them and you go, how in the world can those two gears actually contact one another and actually rotate together? You look at them, they go, those are going not. How does that work? Okay, but it's through the helical arrangement of the tooth, how it twists across. Okay, and having the same profile on both, even though one's larger than the other, they mesh together. They're quieter and give a more positive transfer of power, less backlash, but they're probably 2 or 3 times more expensive, okay, the cost of a spur gear. So, okay, carry more load, operate quiet and smooth, and it develops an end thrust, okay, which means by the shape of it, you know, it actually is kind of pushing against itself, so it actually tends to push the gear toward the end of the shaft. There's a kind of a thrust or a torsional push just by the shape of the tooth there. Other types of gears are called bevel gears and face gears. So a bevel gear usually intersect, okay, at 90 degrees, and special kind of spur gear tooth form, straight gear tooth, and they're kind of tapered from one end to the other. So we can have a speed change, of course, because we have different number of teeth on each one. Face gears, they combine a bevel and spur and pinion, or a bevel and helical pinion. It requires less mounting, carries less load. Let's see. I may have to look that up too. See if we got a face gear. Look on page 694 and you see a herringbone type of gear. So it's like 2 helicals mounted across from each other. So they tend to not push across. Okay, there's your hypoid gears on page 695 that you have in your rear wheel drive automobile. Your differential, it has that type of gear, that hypoid gear. Another set of gears that look like man, those are not going to work together. Those shouldn't work together. Is your crossed helical gear. Okay, so for non-intersecting right angle shafts, and it does not carry much of a load. And whenever you've got to do this arrangement and you don't really have a worm gear type of application that you see at the bottom that would work, then the crossed helical gear would be a choice. So that's what we see here on the screen. Right helical gears. It's pictured on page 695 as well. The hypoid gears, very smooth, strong, and quiet. These have been around, and they're also very unusual looking, how they mate and mesh together. Okay? But if those had not been invented, cars would be very, very noisy with, like a bevel gear type of arrangement. Worm gears, this is the worm. It's basically like a threaded shaft, like a screw, okay? Really big, heavy threads on it. And gears that matches up with it, a tooth that fits into the thread. And so by the twisting and turning of this, turns this, okay? So a counterclockwise motion here develops a clockwise motion up here. And so it's very good for positional type of movement where you need to, move something a desired exact amount, and your power is coming in at right angles. So the worm gear is what powers this, not the other way. This is locked in position into the worm. So the worm turns and pushes this, pushes the gear. Okay? So really power only in one direction. Then rack and pinion, where we convert a rotary motion into a straight line motion. And you've heard of rack and pinion steering, perhaps, that's on cars. So this is the basic arrangement of it. All right? Gives a very precise movement, control, position control, and transfers rotary into a straight line motion. All right, so now let's talk about and look at spur gear design. All right, it's the most basic, most widely used, and you'll run across it more often than you will some of the others, unless you're in a specific type of industry. So spur gear design, the teeth are straight and parallel to the gear shaft axis. They establish a gear profile using an involute curve. Okay, if you look on page 700, there is a method described for you there to create the tooth involute, okay, an involute curve. This is the rotating motion of a point moving about a circle in a specific path. Okay, so involute curve, a spiral curve generated by a point on a cord as it unwinds from the circle. Okay, so it's kind of like taking a string, wrapping it on a shaft, okay, and then kind of a stiff string, and then when you twist the shaft, Okay, it spirals out in a specific pathway. Okay, and it'll always go in that same path. So that's what it's developed off of. So both sides of the gear tooth are formed using that involute curve process. That's what makes it mesh together so smooth and roll together as the teeth come around. All right, we'll take a look at our little gear model back here in just a moment. The basic rule: no fewer than 13 teeth on the running gear and 26 teeth on the mating gear. Okay, so you got kind of a limit to work with. So the pinion, 13 teeth, and then the mating gear, 26 teeth. That's the fewest you can have. Our pressure angle, if you look on page 700, when you design the involute on figure 16.57, there is a 20-degree involute curve being drawn, and so you have a 20-degree tangent line. Okay, it's 20 degrees off of the horizontal at the vertex and at the top there, and that's your pressure angle, and then your curve is developed around that 20-degree angle. Then the consideration of diametral pitch, a ratio equal to the number of teeth on the gear per inch of diameter, okay, of pitch diameter. So it's a ratio of number of teeth to the pitch diameter. Normally a whole number. So it's maximum on gear accuracy. The maximum tooth-to-tooth tolerances allowed are specified in the American Gear Association. Okay, obviously they can't like wedge and be size for size pushed together. There has to be a little bit of open space, a little bit of tolerance there. Creates what we call backlash, but they have to be able to slide together easily as they rotate and roll together. Okay, and so if you look on page too far. On page 697 are all your formula for calculating the various pieces and parts of the gear. Okay, so you'll go through, there is 4 worksheets that you do where you apply these formula to figure out the sizes of the gear components. Okay, the tooth size and various pieces and parts of it. If you look on page 897 with me, you'll see the all the different components of the tooth that the gear manufacturer uses to build the tooth. Okay, so in specifying and figuring out what type of gear to use, you're going to use these calculations. These can all be built into a spreadsheet. I'm going to give you a spreadsheet with 2 or 3 of the formula built into them. Alright, so a challenge is a little bit of a challenge to you to build the rest of the formula in there. Okay, remember, in using a spreadsheet, Excel works in radians, not degrees. So you have to look that up as to how to convert from radians to degrees, because you'll do trig calculations on angles, but the angles, when they're converted from your function, your trig functions, to determine their degrees, they will be in radians. So you have to convert into degrees after that. Okay? The way we draw them, the simplified representation, the end view, we don't draw every tooth. We don't project over and do a true projection. We'll just show an outline of the gear and draw some hidden lines showing the depth of the tooth, okay, the root diameter, and then a center line showing the pitch diameter. Now with you can go to different gear manufacturers' websites and you can pull down gear drawings of their components and insert those in. You can draw each tooth using the method that's shown in the book. Draw one tooth and then array it. We will also represent it like this when there's a casting or a hub, intricate design that we need to dimension. We'll do a cutaway or a section view of it. When you're specifying a gear to be made, to be machined, this is what it would look like. It would have this basic information included on it. And that's on page 699. Okay, showing a gear tooth related to another feature, a little hole will be placed. We call it a timing hole. Okay, and it's lined up with, they says, a tooling hole, and sometimes they call it a timing hole. So this hole would be placed in line with a particular tooth. Usually some kind of tooth representation here, simplified, and then phantom lines, circles drawn representing the rest of the gear teeth is what you're going to see on drawings, unless you draw it using Inventor and you're able to pull in their components, gear actually pulled into your assembly or to your part drawing, and actually it'll have all the teeth drawn and everything for you as a model. Cluster gears are two gears on the same shaft or on the same bore, okay, hub. So you got gear here and a gear here of different number of teeth. So it's represented like that with a whole bunch of center and phantom lines. Gear trains, as we talked about, transfer the motion between shafts. Your gear ratio is important in the gear trains. So it's mainly how many teeth on each one, and you'll do a couple of calculations for those to figure out ratio. It's always to 1. Okay, when you do your calculation, it's a proportion. So if you had 13 teeth on one and 26 on the other, that would be a 2-to-1 ratio. Okay, 2 teeth for 1 tooth, 26 to 13. Rack and pinion drawings, very simplified. You have rack data listed. That's what you put on there. This is the American Gear standard for rack and pinion. Bevel gears, put a little bit more information has to be given for the machinist to manufacture the gear. Worm gears, inside, outside diameter, pitch diameter, face width, and so forth. A little bit less information than the bevel gear for worm gear data. Plastic gears will add various lubricants into the plastic to improve wear resistance. All kinds of benefits from using plastic. Some of them are quite strong. and easy to manufacture. We make a mold, and then we can form numerous gears by actually injection mold process. Okay? All right. That's all I want to mention about gears today.